Now we need to talk about naming complex ions or compounds. And I've written up several examples of complex compounds, and you'll notice that in each case, I place brackets around the inner coordination sphere. That will have an important implication in how we name this compound. Because even though these two compounds are very similar to each other, they both have ammonias and they both have chlorides, they have vastly different names simply because we have chlorines attached directly to the cobalt in this case, whereas up here we do not. And so, let's go through what these particular compounds are called. Now, think back to when we talked about chemical names for ionic compounds. We always say the name of the cation first, followed by the name of the anion. And so in this case, even though we may not know the name of this right away, we know that it will end in chloride because this is the positively charged portion. It has a 3+ charge because there's 3 chlorides. Those will have 3 negative charges there. So this will be 3+. This will just be called chloride. So it's going to be something chloride. This one, same thing, something chloride. Over here, something nitrate. And in this case, we still continue saying the name of the cation first, so we know potassium and then something following that. So just keep that in mind. And don't forget the original rules that we learned before. So, we really just need to know the name of this part. Now, ligands have their own little names. When this is an ammonia group, but when it's bound to a metal, we call it amine. And there's 6 of them. So, we say hexaamine cobalt. 3, because that's the charge of the cobalt, and then chloride. Now, I'm going to write this out and point out something just a little bit odd about naming inorganic complexes. Okay, so you'll notice something, that the A on hexa stays. And for whatever reason, in inorganic complexes, that's the case. We say hexaamine, cobalt 3, and then chloride, because that's the counter ion. Now, I know it's a little odd to have that because there are other times when we're naming, like for example, a inorganic compound that has, 4 things in it, and then an A coming up next. We would truncate that one of the A's, but in this case, we don't, and we keep it. So just keep it in there. Now, this next one, we have 2 different ligands on the metal. Now, we're not going to worry about isomers, even though this one has 2, cis and trans isomers, but we'll ignore that part of the name for now. And we need to know the rules for these 2 ligands. What order do they go in? Do they just go in the way they're written? Well, I try to make it go in that way, but sometimes I might get it out of order. They actually just go in alphabetical order. So, this is an amine, so that will go first, and this is chloro. It's not chloride, chloro. When Complex, when a ligand has a negative charge, it ends in an O when it's a ligand, when it's bound to a metal like this. So just keep that in mind. So the name for this would be tetraamine, because there's 4 amines, and 4 is tetra. Get the pen to work here. Amine has 2 M's. Tetraamine, and then 2 chlorides, so dichloro. Chloro, ends in an O there. And then this is also cobalt 3. So these are -1 charged ligands. And so there's 1, 2, 3 negative charges. So this is cobalt 3. And then still chloride. So just again, notice that this ends in an O when it's a ligand. All right, let's move down to this iron complex. Oh, and also notice that when we're writing the complex, we always write the metal first, but when we're writing the name, we always write it after the ligands. It's just how it's done. So here we have 5 waters as ligands and 1 hydroxide. Now, when water is a ligand, it's called aqua, A-Q-U-A. So this is penta-aqua. Penta-aqua, and then hydroxide, but they have to end in an O, so this is called hydroxo. And then iron. Now, what's the charge on the iron? I have a negative charge ligand here. Hydroxide has 1 negative charge. And I have 2 negative charged counter ions. So that's a +3 charge on the iron to balance out. So iron 3. And then nitrate, because that's the name of the counter ion. Okay, so remember, alphabetical order, don't drop the A, and you may have to look up some of these ligands, and you'll find it in most textbooks or online what the names of various ligands are. But you can probably guess what some of them are. So for example, if we had a bromine here instead of chlorine, you'd just call it bromo. If you had an iodine, you'd call it iodo. If you had a sulfate there, you call it sulfato. Ends in an O, because it's negatively charged. These, the amines, the aqua, they don't end in an O. They're not negatively charged. That's why. All right, so we come down to here. Now, so far we've had the complex be the positive ion, but down here the complex is the negative ion. Those get named slightly differently than when they're a positive ion. We need the complex to end in an ATE, 8. So let's just start off with the part that we definitely know. This is called potassium, and when we have it in an ionic compound, we just say potassium and then name of the negative charge ion, the anion second. So potassium. Now we need to name this. Same story, ligands names come first. There's 6, so hexacyano. Cyano is the name for the cyanide ion when it's a ligand. And then we come to the iron. Now, we want it to end in an ATE. And iron 8, it's just not as good. I suppose it could technically be correct, but there's a better name. We have to just look at the old style of naming compounds then. This is from ferrous, and we tend to use the name ferrate instead, the old style name, because it sounds a little bit better. There may be other reasons, but to me. So ferrate, and then we have to evaluate the charge on it. So cyanide is a negatively charged ligand. There's 6 negative charges. Potassium is a +1 charge on it. So that leaves us with 2 positive charges for the iron. So ferrate 2. So potassium hexacyanoferrate 2. All right, I have another one down here that also contains a negatively charged complex, but we have something else with it. That's this. We have the oxalate ligand. Now, oxalate ligands are bidentate. They're chelating ligands. They attach in more than one spot. They attach in 2 spots. So these get their own special naming system. Instead of di and tri and tetra and all of that, they get bis, tris, and tetrakis. I'm sure there are more beyond that, but generally speaking, you won't encounter ions that have so many on there, because a chelating ligand bonding to an octahedral complex, at a minimum, you're going to attach at 2 points. Octahedral complexes have 6 attachment points, so really you're going to encounter bis and tris ligands more than tetrakis and beyond, just because of space requirements. All right, so let's go ahead and name this. So we start with the positively charged ion first, and that's ammonium. So that's part's done. And then we've got to go in alphabetical order. So this is water ligands right here. And then there's oxalate. Water is called aqua. And this is oxalate. So that starts with an A. That starts with an O. This one should be named first. So it's diaqua because there's 2 of them. And then there are 2 oxalates, but it's chelating, so we call it bis. B-I-S. Oxalato, because again, it's negatively charged. And then we come to the nickel, and it needs to end in an 8, and there's not a very nice way like the iron to go with, so it's just nickelate. And then the charge on the nickel, let's see here. Oxalate is a -2 charged ligand, so there's a -4 right here, but these are +2, so this one must be +2. So nickel 2. So ammonium diaqua bis oxalato nickelate 2. Now we come to an interesting case down here. It is possible to have both of the ions be coordination compounds. There's no rule against it. And so in this case, we have a silver positive ion, and in this case, we have a silver negative ion. Well, what does that do to the name? Well, again, we just name the positively charged ion first, then we name the negatively charged ion. And you'll notice that we'll have to change this to be an 8, ATE, because it's negatively charged. And over here, we won't have to do that. So this is a neutral ligand. So if we look here, we'll have diamine. And then silver 1. Now you might ask yourself, why did he put a 1 there when silver is supposedly always +1? Well, it turns out in general chemistry, a lot of times people tend to lie to you, whether they like to or not. I don't think we actually like doing that, but there are cases when silver has a charge that's different than 1. It's really rare, but it could come up when we're talking about complex ions. It doesn't in this case, but it doesn't hurt to write the charge for a coordination compound. All right, so there's 2 cyanide groups on here. Those have a -1 charge. And then we come to the silver. What do we call it? Well, the old style name for that is argentum. And typically when we have a choice, when adding an ATE to the name, a lot of times the older style name has a more pleasing sound. Iron 8 just doesn't sound as good as ferrate. And in this case, silver 8 wouldn't sound very good, but argentate does, so we call it that. And that similarly also has a +1 charge on it. So, argentate. And now you may know where the iron name comes from, and you may know where, or the symbol, Fe, and you may also now notice where Ag for silver comes from. Argentate. So, that's just a little bit about naming complexes. Now, it's possible to have lots of different ligands on a complex. As you can see here, we only had 2 on here, but I could have added more on, and it's just a matter of making sure they're in alphabetical order and denoting how many of them there are there.